All right, so today we are going to cover root finding methods, okay? Root finding methods falls under this just category of, I guess, I don't know, algorithms or whatever you want to call them, called numerical methods, okay? And these are basically, a numerical method is some way to find a solution to some kind of mathematical problem, but we generally don't try to do it analytically, okay? They're often iterative algorithms that use the power of a computer, and they give you an approximate answer, okay? In often cases, an approximate answer is good enough, okay? So, you know, you guys have taken a bunch of calculus and algebra and all sorts of stuff, and you know, you probably learned that integrals are hard to do, and if you needed to solve a definite integral for some problem, you know, maybe it's too much work to find the analytic solution, okay? So an approximate solution might be good enough, okay? Sometimes you can figure out the exact solution. It might exist theoretically, but maybe computationally that exact solution is too difficult to figure out, okay? And so numerical methods take advantage of the computer's ability to kind of do these things quickly, okay? And then also, we also just know that computers can't even represent like real numbers, right? All the numbers you get, like 0.1, when you type that into a computer, you're only getting an approximation of 0.1 anyway. So we say, well, approximate answers are often good enough, okay? So, you know, one thing that, you know, we kind of take for granted is just the standard normal distribution, right? And I'm not sure if you're aware of this, but the cumulative distribution function, the CDF of the standard normal, has no closed form solution, okay? So, you know, at the back of your stats textbooks, you have that standard normal table, okay? Those are, there's not a closed form solution to get those values, okay? And that's, and in fact, when you type into your computer, so what's the function you type in the computer to get the cumulative density distribution function of the normal distribution? Like if you want to find the area to the left of 1, what's the function you use? So your options are p norm or d norm. P norm, okay? Cumulative distribution function is always p, and then the densities or the mass functions are always d, okay? D for density, and then p for the cumulative, right? Probability, okay? Anyway, when you type in p norm, it's not trying to figure out an exact answer. It's giving you an approximation, okay? And you can read the this paper, okay? And it's an approximate answer to this cumulative distribution function, okay? It's a very good approximation. It's accurate up to like 16 decimal places, which is good enough for most of our things. And in fact, that's like the limit of floating point accuracy anyway. So we say, okay, well, that's good enough, okay? But if you're like, what's the true answer, like the real numbered answer, it's a little bit off, okay? We're not even going to bother with that, but that's just an example of a numeric method where we just say approximate answers are good enough, okay? All right, so today we're talking root finding methods, okay? And so if you got some function f, all right, and we say, you know, f maps from real to real in that you have f of some function, you input a real number and it outputs a real number, right? So that's going to be a real function f. And we say the root of f is where f of x is equal to 0. So basically where this function crosses the x-axis is going to be the root of that function, okay? And a lot of different problems can be expressed as root finding problems, so we have some good applications of this. But today we're just going to focus on how do we solve for where f of x is equal to 0, right? So a lot of times you can just, like if it's simple, you just use algebra, okay? like, for example, if I give you a quadratic polynomial, you would just use your algebra knowledge, okay? And either you'd factor it, or you use the quadratic equation, and you figure out where these where the roots are, okay? And basically, I don't know. So you learned this when you were in like 8th grade or something, 7th grade. Basically, if an analytic solution exists and it's easy to find, use the analytic solution, okay? But if the analytic solution is hard or not possible or something, then that's when you would use a numeric method. Now, for a bunch of these examples, I'm going to use like some quadratic equation, x squared minus 3 or something like that, okay? We would, in real life, we would not use a numeric method to solve for this because that's just silly, okay? We could easily solve those problems. But they're for illustration to kind of show how these things work, okay? Some references for you guys to check out. All right, so the first thing that we're going to talk about, we just got some definitions here, is going to be fixed point iteration, okay? And so I have to describe what a fixed point is, okay? A fixed point is of a function g is where g of x is equal to x, okay? Graphically, you can think of this as you have some function g, and it is where the function crosses the line y equals x, okay? So just imagine the line y equals x running kind of diagonally, and then you've got the function g, and where does it cross? Okay. So because g of x is equal to x, I can kind of continuously apply g of x, and if we're at the fixed point, g of x and g of g of x and g of g of g of x is all the same. They're all equal to x, okay? Just because we're at the fixed point, all right? We also, there's something called, some fixed points are known as attractive or attracting fixed points, okay? And that is if you start off at some value close enough, okay, then what will happen is that if you apply the sequence, it's going to converge to the value a, okay? More formal definition, don't worry about that, okay? So a good example of this is the square root function, right? So if g of x is the square root function, it has an attractive fixed point at 1, okay? Meaning that you can give it any value that's, you know, in the domain of g of x and that. So any value greater than 0, and if you apply the square root function repeatedly, it's going to converge to 1. I don't know if you ever tried this on your calculator when you were in 5th grade. I don't know. I did stuff like this. Okay, I know that's a big surprise. Okay, so all right, so I plug in a big number here, right? And then I say, all right, what's the square root of this? I don't even know how to read this number. What is this? This is 1,234,000,000. Okay, the square root of that is around 35,000. Square root of that is 187. Square root of that, 13.69, 3.7, 1.9, 1.38, 1.17, and I can keep taking the square root of this. Okay, and we can see it gets closer and closer and closer to 1. Can we actually force it to be 1? Oh, look at that. Okay, so at this point the computer says it looks like 1, and it ends up 1, right? And you can see it applied the square root a whole bunch of times. Okay, you can plug in any other number, right? Any positive number. So I can plug in 0.00000, like this, okay? Small number, and I take the square root, and I keep taking the square root, and it gets bigger, and whoops, I hit the wrong button. Okay, go back. Oh, okay, well anyway, I think you guys saw it getting closer to 1 anyway, right? So that's an attractive fixed point. It's the idea that you can apply a function over and over and over again, and it's going to converge to some value, right? So square root of x is a classic function, but there's a bunch of other functions will have attractive fixed points. They might not be as simple as square root of x, but they will also have attractive fixed points. Not every function has an attractive fixed point though, okay? All right, so you start at some initial value, okay, x0, and all you do is you apply the function, okay? And whatever you get, you say that's going to be my next value, okay? And then you repeat and you say whatever my current value, x at time n, if I apply the function g to x at time n, that's going to be my next value, x at time n plus 1, okay? And we do this over and over and over until the difference between x at time n and the previous value, x at time n minus 1, is, if that's less than some tolerance level, e, then we'll stop, right? So if we say it has to be where, you know, the difference is 0, that's probably never going to happen, okay? But if we just say, you know, when it's less than 1 in a million, like 10 to the negative 6, we might say, okay, that's good enough, right? All right, so graphically, this is what it looks like. So here I have the square root of x function in blue, and I just start at the value 10, and I say, well, what's the square root of 10? Square root of 10 is 3.16, and that is the height of this value, okay? That's the height. This is the height of 3.16, and if I follow that to the line y equals x, then this will be my next location. The next location is going to be, I'm going to start at 3.16, okay? So I start at 3.16, and I say, what's the square root of that? That value is 1.77, and I follow that to y equals x, and I say, okay, well, what's the next value, right? And I say 1.7, square root of that is 1.33, and we can repeat this forever and ever, and, you know, after about 15 iterations, we're very close to 1, and we probably have to keep applying this to get values even closer to 1, but we're going to eventually get something close to 1, okay? All right, so if we wanted to use this for root finding, right? So remember the original thing was we want to find out where f of x is equal to 0, and here I've only talked about some function g having an attractive fixed point, okay? Well, we can use this if we can rewrite f of x equal to 0, because that's what we want to solve. We want to find where the function is equal to 0. If we can rewrite this function f of x equal to 0 into the form g of x equal to x, then we can solve for this fixed point, okay? So one example, right, and there's lots of ways to do this, is we could say when f of x equals 0, then this will also be true. G of x is equal to x minus f of x, right? So if g of x is equal to x, then f of x has to be 0 in this equation right here, okay? So we can find the roots of f of x by finding the fixed points of g of x, okay? And there's going to be many ways to do this, right? A lot of times there's multiple ways to figure out how to write a pair of functions so that when f of x equals 0, g of x equals x, and some of them will work and some of them will not, okay? All right, so here is, we're going to look at this function numerous times, okay? We're going to say f of x is equal to log of x minus e to the negative x, okay? We want to solve where f of x is equal to 0, okay? So we're going to say, well, f of x log of x minus e to the negative x is equal to 0, and we're going to rewrite this by solving for x, okay? So I add e to the negative x to both sides, I raise both sides to e, so I have x is equal to e to the negative x, okay? And basically, when g of x is this, if we can say e to the negative x is equal to x, then that means f of x is also going to be 0, okay? Because they're basically the same equation, just expressed a little bit differently, okay? So when this is true, then this also has to be true. So if we can figure out the fixed points of g of x, which is where g of x is equal to x, then we also know f of x will also be 0, okay? All right, and so here's our fixed point iteration algorithm, okay? So here's g of x. G of x is e to the negative x, okay? So I have exp of negative x, okay? I'm going to just start off at some arbitrary location 10, and we're going to call that the old x, okay? And then the next value of x new, is going to be, we apply the function g to the old value, okay? I have iteration 0, and we're going to start counting at 0, okay? and then I have tolerance equal to 1 times 10 to the negative 8, okay? And basically, I have a while loop that says, as long as the new value minus the old value is greater than some tolerance level, keep doing this function, okay? And then the function, or the steps is, take the new value and set that to be the old value, apply the function to the old value, and whatever you get, we call that the new value, okay? And then increment the iterations by 1. All right, does this make sense as far as fixed point iteration? We're just applying the function over and over and over again, but and then we just keep doing this, right? Okay, and so we let that run, and the answer it comes back is 1.3098, okay? And we can say, all right, well, that was, is that really a solution to f of x? F of x is log of x minus e to the negative x. And so if I plug in my solution, 1.3098 here, indeed, I get something very close to 0. Not exactly 0, 9.7 times 10 to the negative 10, but it gives us approximately 0. And so this is approximately our answer, okay? And it took us 19 iterations to get there. All right, this slide, the point of this slide is that if we know that it converges, we can show that the value it converges to is a fixed point, okay? So if we know that x of n does converge to some value a, we can show that a is a fixed point. So a can be thought of as the limit of x of n plus 1 as n goes to infinity. X of n plus 1 is going to be g of x of n, okay? And this is going to be g of the limit of this thing, which is, you know, the limit of this thing itself is a. So we can show that a indeed is a fixed point of g, okay? But the question is, does it always converge, right? So this is under the, if we assume that the fixed point method converges, then it's going to converge to a fixed point. Does it always converge? And the answer is no, okay? Not all functions have attractive fixed points, okay? Some functions have repelling fixed points, or if you apply the function repeatedly, it doesn't converge to a fixed point, it gets farther and farther away, okay? The condition that makes a fixed point attractive is that the derivative at the fixed point has to be less than 1. If the derivative at the fixed point is less than 1, then you have an attractive fixed point, okay? So, so let's revisit this, and I can rewrite this, all right? I can say, well, let's set this equal to 0. I'm going to add x to both sides, okay? And if I do this, then g of x has this form, okay? But at the fixed point, the derivative of this is greater than 1, and this writing g of x here, g of x will not have an attractive fixed point, okay? So even though this statement is true, when g of x is equal to x, f of x equals 0, that statement is true, but our fixed point iteration algorithm will not work because this does not have an attractive fixed point, okay? So if I write g as this, and I run the same algorithm as before, it's not going to converge, okay? And so I actually added one line here. So we're counting the iterations, and I just say if the iterations go over 1,000, break, okay? And this is a good policy to have. Anytime you're doing numeric methods, you should count how many iterations you're doing, and if the iterations hit some limit, maybe a limit that you can set, it should quit, okay? Just so you don't run into infinite loops where you're in a situation where it's not converging, and if you say it must converge, it might run forever, right? So here we've got an iteration limit, 1,000, which is probably way more than necessary. So anyway, after 1,000 iterations or 1,001 iterations, our value is 7,800, and when we plug that in here, we're not anywhere close to 0, okay? And indeed, we reached our iteration limit. So when you do the fixed point iteration, how you rewrite your function, okay? So if we rewrote it this way, how you write it can affect whether it works or not, okay? So we saw one case where it did work and another case where it doesn't. Okay, here we'll look at Newton-Raphson method, and I think in your calculus class you learned like Newton's method, okay? And this is pretty much the same thing, right? Okay, and so Newton's method, what we do is we draw the tangent line to a point, and we say, you know, the tangent line is a good linear approximation of the line itself, right? And that's because, you know, you guys, you don't have to remember this, but, you know, you learn like Taylor series, and you can use all of these combinations of all these derivatives and stuff, and recreate the function to some arbitrary level of precision, and basically here we're just throwing away the second order terms and higher, okay? But so this value is a good approximation around the point, some arbitrary point x0, okay? And so what we do is we just say the tangent line is a good approximation to f near the value x0, and then the next guess that we're going to use is the point where the tangent line crosses the x-axis, okay? So here is some function x squared minus 3. So this is, just imagine a parabola that, you know, dips below the x-axis, okay? And so it's going to cross at like the square root of 3, okay? This is obviously not even scale. The height is 100 and the width is 10, okay? But we're going to start off at some arbitrary point x0 equal to 10, okay? I draw the tangent line, and I follow the tangent line down to the x-axis, okay? And it crosses right here, okay? And so for the next iteration, we're going to say, okay, this will be my x0, and I'm going to go up, and I'm going to say, okay, where is it here? And we're going to draw a tangent line at this location. And we're going to trace that tangent line down to the x-axis, okay? So I started off at 10, we went up to the line, we traced it down to the x-axis. We're going to start here, we're going to draw a line here, come up to here and draw a tangent line. So this is the next slide, okay? And we follow this tangent line down to the x-axis, okay? And that looks like 2 point something, 2.87, I don't know, 2.8. And we come up to here, we're going to draw another tangent line, okay? And we trace that down. And we can see it gets us a lot closer and closer to the root, okay? Where the blue line, the function, crosses the x-axis, okay? So we just run this repeatedly, and this is what we do, okay? All right, so the question is, where does it cross the x-axis, right? Where is this location, right? So what I've done is I've taken this thing and I've labeled this the triangle with rise and run, okay? Because at least in American schools, when we teach slope, we say slope is rise divided by run. I don't know what they say in other countries and in other languages, but we say, you know, the rise divided by the run. And so here the rise is equal to 97. That is the height of the function at x equals 10. So I do 10 squared is 100 minus 3. This value, the function takes on the value of 97. That's the rise here, okay? The run, this is what I want to figure out. How far over do I go here, okay? So if we say slope is equal to rise over run, I can rearrange that to say run is equal to rise divided by slope, okay? So the rise is 97, and the slope is the slope of the tangent line. So the derivative of this is 2x, and I plug in 10 for there, and then my slope is going to be 20, right? So the run is going to be 97 divided by 20, or 4.85. Is that okay for how I figure out the length of the bottom, the run of the triangle? Okay. All right, so then the next value is going to be 10 minus 4.85, okay? So that's what we have, okay? We got 10 minus the run, which is, you know, 97 over 20, and we get 5.15. Or, you know, more generally, okay, I take in that value x0 and I subtract off f of x0 divided by f prime of x0, okay? And this is going to give me the value x1 to use at the next iteration. Okay, and then we can just repeat this for the next guess x2, and then in general, if we are currently at location x at time n, then the next value we use, x at time n plus 1, is going to be xn minus f of xn divided by f prime of xn. Okay. So that's what we got there. Okay, so here's the Newton-Raphson algorithm. Start at some initial value x0, and then just apply this thing to get the next value, and you repeat, and you keep going until the value of the function is very close to 0. Okay, so we want to find where the function itself is equal to 0, but maybe not perfectly, and so we just set some arbitrary tolerance, and we say, you know, when the function itself is very close to 0, that's when we can stop. Okay, so here we'll say our function is this log of x minus e to the negative x, and we can say, all right, well, what's the derivative? Because we need to figure that out, right? So the derivative of log of x is 1 over x. Derivative of e to the x is e to the x, but we apply chain rule, which is -1 here, so it becomes plus e to the negative x. Okay, so the only drawback of Newton-Raphson method is that you have to figure out the derivative, which in some cases is hard to do. Okay, generally taking derivatives is easier than taking integrals, but in some cases the derivative, you know, you might not be able to solve for that either. Okay, so Newton-Raphson method does require you to find the derivative, but maybe it's not possible. Okay, all right, so anyway, we got f and we have f prime. So I have f is log of x minus e to the negative x, and f prime is 1 over x plus e to the negative x. Okay, so I have two functions for this, and then I apply the algorithm. Okay, so we're going to just say while f of x is greater than some tolerance, and here we're going to say it's got to be less than 1 times 10 to the negative 8, we're going to say the next value of x is going to be our current value of x minus f of x divided by f prime of x. Okay, so all I'm doing is coding exactly this, x minus f of x divided by f prime of x. Okay, and then we just iterate the number of iterations. We just count up. Okay, and so here I started off at some arbitrary location 2, and I get the value. The approximate root is 1.3098. Okay. And if I plug that in, indeed I get a value very close to 0, okay? Negative 3.49 times 10 to the negative 9, okay? And it only took us 4 iterations to reach this value, okay? So Newton-Raphson often converges very quickly. All right. If we assume that it converges, we can show that the value it converges to is a root, okay? And so maybe I won't go through all of this, but basically, if you follow this, it's going to be a is equal to a minus f of a of this, and this is only going to be true when f of a is 0, therefore it has to be a root, okay? Does Newton-Raphson always converge, though? And the answer is no, okay? And so you can read through this slide and this slide, but basically, if while in the steps of doing your iterations and calculations, if the slope ever ends up 0, or even like very close to 0, it's probably going to break your algorithm. Okay, obviously, you know, because we're doing f of the value divided by f prime, and if f prime is ever 0, it's going to break. Okay, now that's not to say that the function is not allowed to ever have a local min or local max. Okay, you can have derivatives equal to 0. It's just that in your sequence of iterations, your iterative steps is not allowed to end up at some location where the derivative is equal to 0. Okay, so if in your sequence of steps you happen upon a location where the derivative is equal to 0, maybe you just change your starting location, and maybe you'll avoid that spot. Okay, so it's fine to have derivative equal to 0, but just not at one of the locations in your iterations. Okay, convergence depends on the initial guess. And so depending on where you start, you can end up with different answers. Sometimes you're in a situation where the locations oscillate back and forth, and that causes problems, okay? And then you've got other scenarios that also can cause problems, okay? Let me show you some things. Okay, so here's, this is pretty much kind of like the illustration I did, where it's just kind of following and it's following that. So this one has no problem. But this one, okay, so we start and it's tracing, and we can see it kind of bounces around. So it, it starts here, and it takes the it takes the derivative, or the tangent line. It comes down here, and when you take the tangent line, you end up even farther away. So you're going back and forth, and you keep ending farther and farther away from the root. So sometimes that can happen. There's no guarantee from Newton-Raphson, okay, that it's going to converge. All right, let's take a look at secant method, okay? So secant method is similar to Newton-Raphson method, all right? But you might say, well, I don't want to do Newton-Raphson method because I got to figure out a derivative, right? So sometimes this happens, right? You have a function, you don't want to bother figuring out the derivative, okay? Well, you can use secant method, all right? And so secant method, what it does is we say, all right, well, let's start off with two locations. Let's start off at x0 and x1, okay? And we're going to draw, we're going to graph it, and we're going to find out where the function is at x0. We're going to find out the value of the function at x1, and we're going to draw a line that connects x0 and x1. And depending on what your function looks like, the line that connects x0 and x1 might be a good linear approximation. It could be like a tangent line, okay? But we call it a secant line because it's not tangent. It just crosses 2 points here. So here is kind of our same problem, x squared minus 3. We're going to start off at just arbitrary locations 10 and 8, okay? So here is the value of the function at 10. Here's the value of the function at 8, okay? And I draw a straight line that connects 10 and 8, okay? And so I trace this all the way down, and I trace that line until it reaches the x-axis, okay? And I say, all right, it crosses the x-axis right here, and therefore the next value I'm going to use is right here, okay? So this looks quite similar to Newton's method, except Newton's method we drew a tangent line which has a steeper slope, and it ended up kind of ending up over here, okay? But here you can, I don't know, you can barely see it, but it kind of crosses the function itself, okay? It's going to be more apparent on the next slide. Okay, so anyway, I have this location 10 and 8. We draw a line that connects it, we trace it down to the x-axis, and we say, okay, this is the location I'm going to use for the next point, okay? And so right here, I draw a point there, and I use the last point I had. So I have this point, and I draw a secant line that connects those 2 points, and I continue that line until it reaches the x-axis again, okay? And then so right here, I'm going to use this next location. I come up to here, and I'm going to draw a line that connects from this dot to this location, and I trace that down to the x-axis, and I keep going, so on and so forth. Okay, does that kind of make sense? All right, so here I did not need to calculate any derivatives. Okay, I just need to calculate 2 points, and I draw a straight line that connects them. Okay, all right, so how do we figure out where this line crosses the x-axis? Okay, well, we say we got to figure out kind of this triangle here, and we're going to kind of trace that out, right? So we say, you know, the slope of this secant line is going to be equal to basically the change in y between these 2 points and the change in x and the 2 points, right? So the change in y is f of x1 minus f of x0, and the change in x is x1 minus x0. Okay, so for our points, we had 10 and 97 because our function is x squared minus 3. So x0 is 10, f of 10 is 97, x1 is 8, and f of 10, this f of 8 is 61. So 8 squared is 64, 64 minus 3 is 61. Okay, so 61 minus 97 divided by 8 minus 10 is equal to 18. Okay, and so we know that the line passes through the point 861. So if you remember point slope form, which is y minus, you know, f and, you know, times m minus this, we're going to plug in y minus 61 is equal to 18 minus x minus 8. Okay, and then we're going to solve for x when y is equal to 0. Okay, so I plug in y equal to 0, solve for x, and I get x is equal to 8 minus 61 divided by 1 over 18, right? So this is our x1. This is my f of x1 times 1 over the slope. Okay, and that's going to be my next value. So my next guess I use is 4.611. All right, so more generally, this is the slope. Slope is the change in y over the change in x. Okay, and then in point slope form, it's going to take in this form, and if we solve for y, when y equals 0, we're going to get this. Okay, so just kind of more generally, we can say the next iteration value that you have is our current value. Okay, and then basically the difference between xn and the previous value, and then f of xn minus the previous value there as well. Okay, and so this is you can apply the secant method to do this, and you can avoid taking derivatives in the first place, right? One thing to note, I know in my picture I had the case where your secant lines connect like this, okay? And you do this, okay? But it's also fine if you have x0 here and x1 over here. This is also okay, all right? So you just draw a secant line that connects these two, okay? And then you would just say, okay, well, x2 is going to be right here, where the line crosses the x-axis, and then you just draw a secant line, okay? And this is going to be x3, and you connect these two like this. Okay, so x2 and x3 are here, and then you connect that, and you can see you're going to get something quite close to the actual root. So it's not a problem if x1 and x2 end up on one is positive and one is negative. That's not an issue. I know the picture that I had, they both started off positive like this, okay, but it's not a problem if one is positive and one's negative. Okay, secant method will still work there. And it's still going to have this exact form as well. Okay, so this is just kind of the one slide for the secant method algorithm. All right. And the way it converges is also similar to Newton-Raphson method. And just like Newton-Raphson method, it's not guaranteed to converge. Okay, but the advantage with secant method is that you don't have to figure out the derivative, okay? The disadvantage is you got to calculate the value of the function in two locations. Okay, the last method is the bisection method, okay? This is, it's very simple. It's a little bit slow, but this one is guaranteed to work, okay? So the other methods, it might not converge. Bisection method is guaranteed to converge to find a root, okay? And all it requires is that you bracket the root, okay? So you just, you have to find, the function has to be continuous, okay? That's rule one. Rule one, function has to be continuous, and then you just pick an arbitrary left and a right bound, okay? And the rule is that the left and right bounds, the value of the function at the left and right bounds, have to have opposite signs. So either the left side is negative and the right side is positive, and you know that the function will have a root in between the left and right, or the left side is positive and the right side is negative, and you know that there has to be a root between the left and right side. Okay? And so, you can just do a quick check. You can say, what's the value of the function at the left? What's the value of the function at the right? You multiply those two together, and if they have opposite signs, that value is going to be negative. Okay? And if there's a root in between there, then you can apply bisection method. Okay? And so the way bisection method works is okay, so here's our x-axis, and we've got, you know, some function like this. You draw an arbitrary, you know, left bound. Okay, so we'll call this x on the left. Whoops, what happened here? And then we've got x on the right. Okay, and then you calculate the midpoint. Okay, all right. And so x on the left is negative, x on the right is positive, and then you say, okay, at the midpoint, what is this value? Well, this value is positive. Okay, and so basically you just keep the left and the right side so that that we know that there's a root. So we know that there's no root, so we're going to just throw this side away. Okay, and then we calculate the midpoint of this again. Okay, and the value of the function here is negative. Okay, and so we say, okay, well, the root has to be in between this side and this side, so we throw this side away. Okay, and then I take the midpoint, I cut it in half, and I say, well, what is the value of the function here? And this is positive. Okay, so then I throw this side away. Okay, and I keep going back and forth, right? Or not back and forth, but I keep taking the midpoint and cutting it in half, and then throwing away the side. It's just so that we always have one side negative and one side positive. Okay, and so we keep having our interval, and that is how we're going to find it. Okay, so this is how the bisection algorithm works, right? We're going to just say, first of all, if the left and the right side are super close together, okay, like below some tolerance level that we've specified, then we can go ahead and stop, right? Okay, otherwise, we find the midpoint, okay? So we just take xl plus xr divided by 2. You just find the mean of your left and right bounds, okay? And if the mean happens, like if you happen to get equal to 0, then stop, okay? Otherwise, calculate which two have the opposite signs, right? So you're going to do the value of the function on the left multiplied by the value of the function on the, of the midpoint, okay? So you say function on the left, value of the function on the left times value of the function at the midpoint. If that is less than 0, then that means xl and xm, those have opposite sides, opposite signs. If the value of the function on the left and the value of the function of the midpoint have opposite signs, then it's going to come back to 0, and therefore we're going to replace the right-hand bound with the midpoint. Okay. Otherwise, we're going to replace the left-hand point with the midpoint. Okay. And so that way we can make sure that the two sides of the interval, the value of the function, have opposite signs. Okay. And then we just repeat. Okay. And so this is just the explanation there, right? Okay, so here is our same function, log of x, negative e to the negative x, okay? So this is the value of the function. We just start off at some arbitrary locations 1 and 2, and I say the tolerance is going to be 10 to the negative 8, okay? We find the value of the function on the left, value of the function on the right, and we say, do those have opposite signs? And indeed they do. Value of the function on the left and value of the function on the right indeed is less than 0. Okay, and here's the algorithm. Okay, we start off with iterations equal to 0, and our while loop is we say while the right side boundary minus the left side boundary is greater than 0. Okay, I'm not greater than 0, greater than our tolerance. Keep running this. Okay, so we calculate the midpoint by doing finding the mean of the left and right. And we find the value of the function at the midpoint, okay? All right, and then here, what does this statement do? Why do I do an all equal f at the midpoint 0? What does that do? Okay, so all equal is our alternative to using equal, right? So if I did f at the midpoint equal 0, I'm probably never going to actually hit 0 exactly, because because we saw with machine error and stuff, you're not going to get exact values, right? 0.1 plus 0.2 equals 0.3 is false, okay? So all equal says, you know, if they're close enough, then return true, okay? Now I wrap that in identical true because all equal will return true if these are approximately equal, but then when it's wrong, when it's false, it returns back this string, okay? It returns back a string, which is not what we want, okay? So we're going to do that, and if it's the case that they're equal, we'll stop, okay? Otherwise, we'll just check, is the left times the midpoint values, is that less than 0? Meaning, do they have different signs? If they have different signs, the midpoint becomes our new right bound, okay? Otherwise, the midpoint becomes our left bound, okay? And then we'll increment our iterations, and we just repeat this over and over and over again, okay? And then after we're done, the value we'll use will be the midpoint of my left and right bounds, which is going to be 1.3098, okay? Which was the same value there. Okay, so we'll end here for today. And again, I will not be here on Friday. I'll record a short video for you guys to watch, just covering a few last topics. I'll also release homework 5, and we will see you guys next week, which is week 8. So that's time's going rapidly. All right, we'll see you then.